welcome to my weekly video of something I found interesting in the world of astronomy. And this time will be some research from the Hayabusa 2 mission. I've talked about Hayabusa 2 before, but in brief, the Japanese space agency JAXA sent a craft to the asteroid Ryugu to examine its surface and to collect samples of material. The way it collected the samples was to fire missiles at the surface of the asteroid. Material would be kicked up and go into a horn structure, which meant it could be collected and sealed and sent back to Earth. It did this a few times with small projectiles, but the big one was a copper projectile fired at around 2 kilometers per second at the surface on the 5th of April 2019. Now this should give us some interesting science when the probe returns, but there's something more immediate we can do, and this week a paper published in the journal Science shows how researchers examined the image data taken during and shortly after that impact to find out more about the surface of Ryugu. You see, if you think about it, it's quite logical. Imagine firing bullets at different plates and different materials. You could get some understanding of the type of material you're dealing with from how the impact forms. Glass shatters, rock dents and craters, sand forms a different sort of crater to rock, soil forms a slightly different crater to sand, jelly does really weird stuff, and other things like that. You can start figuring out stuff about your material from what happens when you hit it with a projectile. So maybe we can get some understanding of the surface of Ryugu from examining what happens when you fire a lump of copper at it. So what do the researchers find? Well, they use images from the impact to generate a 3D model of what the impact site looked like, as and after the crater was made. They got a shape that was roughly semicircular, which the researchers attribute to a large block of rocks southeast of the impact point. They estimate the depth of the pit and its diameter. They can also look at images taken of the ejector during the time after impact, looking at rays of ejector coming out of the point of impact, and what's called the ejector curtain, a cloud of ejector near the impact site. So the next question is, what could they find out from this? You see, our initial views of Ryugu suggested a layer of regolith material which covers the surface, with large boulders strewn about the surface. And we can find out what holds this regolith together based on the impact. Is it held together by its own strength, or is it held together by gravity from the asteroid? And one important point from this is the ejector curtain. We expect that if the asteroid is held together by gravity, the curtain won't disconnect from the surface. But if it's strength dominated, like the materials dominated by the strength of materials in it, it should rise off the surface. The fact that the ejector curtain here doesn't leave the surface in the images taken after the missile was fired suggests a loose regolith dominated by gravity from the asteroid. And we have a theoretical formula for how large a crater should be in the gravity-dominated regime, depending on the density of the target, as well as the mass, radius, density and impact velocity of the impactor. And of course, this idea of strength versus gravity and all of this stuff can be tested in laboratories on Earth, which means we get this formula with a few empirical parameters, plug in the value of gravity on Ryugu, and get an idea for how big your crater should be, what the crater radius is. And that fits quite well, according to these researchers, with what they found. So the evidence they presented suggests this gravity-dominated model. Finally, the researchers point out the implications of this on the age of Ryugu's surface. You see, there's a reasonable way to estimate the age of an asteroid, given its size and what we know about the collisional and dynamical history of the asteroid belt. It's insanely complicated, so I'm not going to go into the detail. I'm not really sure I understand it. But the short is we can get an estimate of an asteroid's age from its size. And, of course, a few other features of its surface which we'd seen from images of Ryugu earlier. However, this relation does depend on composition. This is why that bit about gravity-dominated and strength-dominated is so important for this. We get an estimate of around 158 million years plus or minus 47 million years for a strength-dominated, like dry soil with some cohesion, and one of 8.9 plus or minus about 2.5 million years for a gravity-dominated surface. The evidence given earlier then supports the gravity-dominated regolith and therefore the age of around 8.9 million years. As usual, I'll give a link to the paper in the description. I hope you enjoyed this. I hope you enjoyed learning about what we found out about this asteroid, and an interesting way to find out about the age of an asteroid. Till next time, goodbye.